Welcome, everyone. My name is Heather Mellish, and I lead our Edge go-to-market services team here at AWS. Thank you for attending our session on maintaining availability with global services. Today, I'm joined by three members of our principal engineering team with our Edge services. I'll let you all introduce yourself. Harvo, why don't we start with you?
Hello, my name is Harvo Jones. I'm a principal engineer with Edge Services. I work with Global Accelerator. It's a UDP TCP proxy service. I also work with internet monitoring and internet control across our global network.
My name is Gavin McCullough. I'm a principal engineer in Edge Services, but specifically in the Route 53 organization. So we own the domain DNS services, the VPC resolver, and the public DNS service for AWS. And we also own operations of most of Amazon's DNS, Amazon and AWS's DNS as well.
My name is Jorge Vasquez. I'm a principal engineer with Amazon CloudFront. We are a content delivery network, which means my job is to deliver more bytes in fewer milliseconds for our customers.
Thank you all for joining us today. So as we kick off our session today, let's start with the title of our session, availability. As we look across all three of your respective services, what's the importance of availability? Georgie, why don't we start with you?
Right. So at AWS, we have our set of priorities very well defined. Our first priority is security, of course. If things are not secure, if we can get a problem in that area, nothing else can be trusted. The second priority is durability, which means the data you entrust us, we cannot lose that data. We have to keep it pretty much forever. And the third one is availability. And after those three fundamentals comes everything else: performance, features, ease of use, anything else you can think of. It might not look like much that availability is number third, but it's right there in this elite set of things we care about. And why is that? The reason for that is because, and that's especially true of the services that we here work on, the so-called services that operate at the edge of the network, our services are foundational parts for everything else. So a joke that we have with new hires is that, look, if you don't do your job well, it's all going to be okay, except that your friends and relatives are going to read on the news that the internet went down, right? So it's not about our services going down. It's about folks like Slack or Snap or Hulu going out of service, right? So we don't want that. Availability is fundamental for us in that sense because people depend on us to do their own business.
So, adding to what Georgie was saying there, so Route 53's point of view, I guess, in this is we're a little bit unusual in that we, even among the AWS services, we offer a 100% availability SLA. And that's, if you think about like the reality of DNS is involved in almost every connection you make right at the start. And if the DNS request were to fail, the connection can't go ahead. So it is a super critical service from the perspective of all kinds of applications. And so for that reason, we take availability extremely seriously. And that is how we end up at the 100% SLA. Harvo?
So I guess the first place I would start thinking about it is at the network level. Georgie mentioned that security was paramount. Between any of the links that span Amazon facilities, we have link level encryption, AES 256-bit. On top of that, working with internet monitoring, it's all about measuring availability. So what is the perspective of availability from our customers' point of view, folks on the internet trying to use our services, and from our services own point of view? You have internet monitoring and internet control, which takes those signals, those measurements, and tries to steer around availability impairments. And I guess the next level would be to think about the service itself running on top of this network. So with Global Accelerator, CloudFront, Route 53, all of our services are delivering bytes to customers on the internet. And so with Global Accelerator being another one of those, what we do is we load balance our customers' traffic across endpoints that are available. We ingest Route 53 health checks, and we also make sure to do so in a manner that's fairly statically stable. meaning if we're not getting these Route 53 health checks that I mentioned, we continue to route connections, TCP or UDP, toward your endpoints.
I think one other thing to add on that, one of the things that Route 53 does in order to try to meet that is historically DNS is built with a lot of redundancy into it. So the idea is that you can have a domain name and you can have multiple name servers for it. And if one of the name servers fails, life can go on because the other ones will take over and it's no problem. And that's designed into DNS from the start. And for a long time in the early stage of the internet, people would use like multiple different, people would partner up and host each other's DNS and that kind of thing, so that you had like, well, if we fail, you'll keep our DNS going, that kind of thing. So how Route 53 looks at this is kind of like extending this into the modern day. It's difficult to use multiple vendors in DNS a lot of the time because a lot of the nicer features, the more advanced features in DNS are not common to multiple providers. So what Route 53 aims to do is to offer, we give every customer 4 name servers, and they are run as 4 different DNS services. So we have, roughly speaking, 200 edge pops across the world, and wherever you are in the world, you're being served by the 4 nearest to you. So, and so essentially what we're running is, we're not really running one big DNS service. We're running 4 DNS services. And when we need to do a deployment, we'll deploy to the first one, then the second one, then the third one. When we need to do operations, we do the same story. So we're aiming to give you that multiple different DNS services that are independent from each other all the time, but keep them consistent so that you have the right data on them all.
That's actually a very good point to dovetail off of. Global Accelerator follows the exact same pattern. It's separate data planes. We call them network zones. When you go ahead and spin up one of your accelerators, you have an IP address which is associated with one of those network zones. So these are independent physical infrastructure backing these network zones. And we go a little bit further. When you zoom into the servers behind one of these zones, we try to make sure that we shuffle the number of servers that are backing any given customer's accelerator from a neighboring customer. So to give you that minimized overlap between customers.
Georgie, you made reference earlier to durability, reliability, and availability. How do you all differentiate between durability, reliability, and availability?
Right. So durability is the persistence of data, right? Is this data still there or not after you save it or you store it or you give it to a service, right? Is it durable? Availability is the service, can the service be used? So the fraction of the time, the percentage of the time that the service could be used. Reliability is a little bit trickier on that because it's a measurement of how long can it be used without interruptions. And that one has different levels of importance for different services. So for example, for DNS, the reliability is not as important as availability because the transaction you do with a DNS server is very, very short dured. You send usually one UDP packet, you get one back, and you're done. You have your IP addresses, you can go on and make your connections. Similarly, if you're using either AGA or CloudFront to make an API call, it's not going to be as short as DNS, but it's also going to be, you're talking about milliseconds, right? On the other hand, if you're doing something like playing an online game through AGA, right? And AGA happens to have a blip and send you to another edge location, the service is pretty much available 100% of the time, but then you got disconnected from your game and you have to start a new round, and that's a very frustrating experience, right? Similarly, in CloudFront, if you're running a long download and your download breaks, you have to start it over. It's also frustrating. So for those types of workloads, reliability becomes really, really important. And pretty much for these applications, reliability kind of folds into availability because the application itself doesn't really work, right? If you keep disconnecting and reconnecting, the application doesn't make sense anymore. And by the way, that's a theme that you see a lot when you start diving deep into availability, right? Some characteristics that usually we do not consider availability sometimes become fundamental to the service. Like one example is right now, like the people watching us are probably watching a video, streaming a video, right? If you don't have enough throughput to deliver this video, even if the connection is there and we can still do some TCP packets back and forth, the service might as well be unavailable because they cannot do what they want to do. Right. So is that performance, is that availability, it kind of crosses over a little bit. So sometimes we find ourselves in these hard to define places.
I've often thought of performance degradation as a slippery slope into an availability problem.
And everyone will define the line somewhere slightly different. Yeah.
Availability is always at the top of our customers' requirements. Gavin, how do you measure availability?
A combination typically of passive and active checks. So like any application, our DNS service and our APIs are instrumented and reporting tons and tons of different metrics. Like, for example, obviously obvious things like CPU and memory and things like that. They don't really contribute to the availability directly, but they're indications of the health of the service. We also monitor any kind of error rate or packet loss rate or anything like that the hosts themselves are aware of. But I think what's probably typically more effective is using active monitoring. So where we're essentially building secondary systems which are constantly probing so we have a network of probes to match the network of DNS servers all around the world that are constantly pretending to be customers, sending queries and making sure that we're doing the right thing. And if you look at our own, we have to, in our own metrics, we have to exclude our monitoring traffic as part of our work because it's actually a significant amount of our overall traffic. I won't guess at a number, but it's a significant portion of our overall traffic is actually just synthetic monitoring traffic that's constantly making sure that we're A, answering the query, and B, answering it in a timely fashion.
I could probably add to that a little bit. Similar to the active probes that Gavin was mentioning, we participate with real user measurement systems. So clients on the internet. From those clients, probes are being sent to all of our services, CloudFront, Global Accelerator, and we're collecting those measurements to gain a perspective of what they're seeing. And availability itself, it's not just a binary signal, good or bad. It can degrade and degrade differently for different populations of clients. So you might have folks in Comcast in San Diego or folks using Telenor in Oslo, Norway, having a different experience. So when we talk about our expansive global network, we're collecting measurements from all these different populations. And we also have to do analysis on this large volume of metrics. And then from that analysis, we can feed it to our automated systems to try to maintain availability, or to feed it to our operators to take manual action if need be.
Yeah. Expanding on that non-binary nature of availability, when you're dealing with real user monitoring systems, one thing that comes to mind, and I was remembered of that when I finally came into an office building after quite a long time, like many of us, is that this system is not 100%. It's not super clean like the systems that you get from synthetic monitoring. So I walked into the elevator and whatever I was doing on my phone stopped working. So my phone probably registered an availability drop at that point, but it's not the services that I was trying to access fault, right? It's because I decided to walk into an elevator. So at this point, availability becomes a probabilistic signal, and we have to walk through that and set the thresholds at a level that makes sense for us.
Yeah, I think one of the things that's actually interesting when you gather the huge numbers of metrics that we do, one of the harder parts often is summarizing them into a thing that you can reasonably review and take in. Like if you have 500 metrics, and we have way more than 500 metrics, really what you want is, every week we have an operations meeting where we look at graphs and we check everything is as we expect it to be, and producing the aggregate graph. Like, so we will typically look for things like in propagation monitoring, we don't want to look at the average propagation time. We want to look at the P100 propagation time. What was the very last host to get the change? And thinking of, so all of these metrics need that kind of aggregation and people thinking through and designing how that works, so that you can look at the right signal rather than 1,000 signals.
If you think about cities and autonomous systems, that pairing, it would take roughly 10,000 of those to account for around 90% of total traffic. Think of humans trying to configure 10,000 different monitors.
Right.
In and around our services, we're talking a lot about static stability. Harvo, what is that and why is it important for our customers?
Right. Static stability. When I think of it, I'd probably start with our data plane. There's the concept of having our control planes decoupled from our data plane. The data plane being the primary main focus, main purpose of your service. So routing customer connections for Global Accelerator, handling HTTP requests or DNS queries. When I think of static stability, it's the ability of those data planes to continue to serve traffic, to continue to carry out their primary function in the face of failures external to them. So these systems need customer configuration. When customers want to spin up new distributions or define new hosted zones, or when customers want to change those config properties. So when I think of static stability, I think of imagine the delivery of those configuration updates completely stopping. The data plane should not care one bit. It should continue on with its prior state of the world and continue handling customer connections. One part I would add is the way Global Accelerator knows which endpoints are healthy is from Route 53 health checks. So we're routing around failures. If that ingestion of health checks stop, we just have the last list of known healthy endpoints. We keep that static, and we continue routing connections.
I think one of the tricks that we tend to use, and I think you'll see it in a lot of these systems, is to try to keep things as simple to reason about and simple to operate as possible. And often the best way to do that is to decouple the different things that are going on. So within one of our DNS servers, we have a DNS server that is answering DNS requests, reading from a large data store or data stores, which are being propagated in real time. But we don't have that DNS server also involved in the propagation. It just reads from the data store, answers the queries. That's it. And then we have a separate process running there that is pulling in the changes and patching the data store. And so if something goes wrong on that propagation system, the DNS service will just keep going, keep reading from its data store.
And these kinds of data plane services, they don't even do simple things, like they don't even write their own log files or emit their own metrics. Right. They do the minimum amount of output possible for other systems to do those things. Right. So they can be as simple as possible.
So these edge components are statically stable, meaning that they keep on going even if they can't get new updates from the control plane, which customers use to make changes quickly. Georgie, why do our customers need to make changes quickly?
Yeah, so you think about it, it goes back to that foundational nature of the services that we were talking about before, right? So imagine, for example, that you're running an e-commerce website, and in a very big day for you, some part of your internal systems fail and customers cannot place orders, right? You have two choices. You can keep going and display an ugly error page with computer stuff for non-tech users, right? Or you can go to a system like CloudFront and make a change to send those users to see a dog, right? So that's an extreme case, but that's a way to maneuver, right? Another situation could be you're launching something globally, right? And we have various examples of things that are launched at a given time, or a show that goes available to buy tickets, or any of those things that have a time component to them. Customers don't want to wait, it's going to be available for some people now, for some people 4 hours from now. That would be a nightmare for whoever is running that ticket sale, right? So customers need to make those changes because their business cannot wait forever for changes to take place.
I can imagine customers wanting to spin up new infrastructure for changes in demand, or using application load balancers behind their accelerators. And those load balancers themselves scale out their nodes as load increases. And in both cases, it involves the delivery of configuration rapidly to the edge, so the data plane knows how to route to all those new endpoints.
Yeah, I think it's one of the really interesting developments over the last. I'm going to show my age now, but over the last 15 or 20 years, like if you were working in this industry 15 or 20 years ago, and you wanted to set up a web service with a website, it took not hours, days, weeks, because there were so many things that you had to do, and things moved at relatively slow pace. But now with cloud computing, where we're at is a situation where you can call a bunch of APIs. You can use infrastructure as code like CloudFormation or Terraform, something like that, and rebuild an entire infrastructure in 10 or 15 minutes. Every time somebody launches a new ELB or ODS database or CloudFront distribution or AGA, there is a DNS change happens as part of that. And people will spin up an entire piece of infrastructure to test something for 20 minutes and then tear it down again because you're paying by the second. So why would you keep it up any longer? So I guess it starts to become about productivity almost, that people want to move very, very, very fast. And so it's really important that we can make changes on behalf of customers really quickly.
And let's not forget that it's not just customers, right? We also have to make changes ourselves when we operate the system. Harvo was talking a little moment ago about that fine-grained monitoring that we do. Sometimes we need to shut down parts of our infrastructure because some parts of the network connecting to some ISP somewhere is not working. It might not be your fault. Might be your fault. Doesn't really matter. We have to shut it down and route the traffic somewhere else. Some of that is automated. Most of it is automated, but some weird extreme cases might not be. And for those, the person waking up at 3 a.m. because their alarm went up should be able to very quickly make a change so that our customers don't suffer through it.
Well, the problem with these global changes is that they're global, and change by definition introduces a lack of order, let's say, in our systems, and they create an opportunity to disrupt that static stability that we were speaking about earlier. Unlike code changes that we can roll out slowly, customer changes and some of our internal operational changes, they have to go out everywhere quickly. So they present a risk for disrupting that static stability. Harvo, can you elaborate on why this is?
Right. So why pushing out global changes quickly disrupts static stability? So the premise of the question is right, and we can compare it to software deployments, which happen in a controlled fashion, a controlled and monitored fashion, which is also well tested. Oftentimes, with customer configuration, these are configurations that customers have chosen to put in place right now. So these might be configurations that we haven't had a lot of testing around, and this is delivered to a large number of our data plane, a large portion of our data plane really quickly. And so really this introduction of rapid global changes is kind of the antonym to static stability. And it allows our software at the edge to operate with configurations, like combinations of configurations we might not have thought of, which can introduce things such as poison pills. Yeah.
Okay, so let me expand on that. So poison pills is a term that we use that basically means one of those configurations that causes the software at the edge or the configuration at the edge, the whole system that is taking that data to behave in some kind of unexpected manner, right? And that can come in many forms, and some of them can be quite surprising. One simple form is a file that cannot be parsed, right? And then you have an error. But sometimes the file can be parsed, and then we ingest a value, let's say it's a 0, and somewhere down the line your code divides by that value. Boom, like you have a crash because you try to divide by 0, right? And the permutations there is infinite, right? There's infinite ways of breaking software, as we very well know, right? So and this can happen at various stages, right? So they can happen in ingestion, they can happen in usage, and they can happen very late when some very special request comes to your data plane. So it doesn't necessarily come right away. It can be a special combination too.
Yeah, I think I know Route 53 has the same problem. So you can think of it, I mentioned before that we have 4 distinct data planes, and we like to operate them one at a time and leave space between. So we make the change to the first one, then the second one, then the third one, then the fourth one. But customers don't really allow us to do that. So we have to get the change to all 4 of them, within our goal is typically in well under a minute. So you don't really have that kind of option to go slowly, unfortunately.
What can we do about these poison pills, Georgie, that you were talking about earlier?
Yeah, so we have developed over the time quite a few ways to deal with them, right? One would be to simply add tons and tons of validation, right? So a phrase that Harvard coined is have belts and suspenders, right? So before publishing these new changes, validate them. Before ingesting, validate them. Before using, validate them again. So don't be shy. Write multiple validations, even if they seem the same, because chances are that since you're writing them in different systems, they're going to be slightly different. They might be in different languages. They might use different libraries. And that diversity helps you catch problems, right? Have other person write the second validation, don't write it yourself, right? That's one simple one. Another one is a system we call food tasting, which is a system that it's a design pattern in which we get that change, and instead of consuming it right away worldwide in all the data planes, we do one of 2 things. One, we can give that same change to a synthetic copy of the process. So imagine it's a DNS server. So we spin up another DNS server on the same physical server. We give the configuration and then we blast it with synthetic DNS requests, right? If it crashes, we don't give that same set of changes to the official one, the one that is answering question for our customers, right? That takes a little bit of time. It takes 5-10 seconds, but we think it's worthwhile. In other cases, I think AGA does that. Instead of sending it to a synthetic version, a mini server, you send it to a fraction of your fleet. And in that fraction of the fleet, if it survives after a few seconds, well, then you can give it to the rest of your fleet. If it starts having problems, then you have to back off and then stop the propagation of changes.
The way I would probably summarize how we approach poison pills is, first, you want to stop them from occurring in the first place. Test rigorously. That's going to fail, right? So if they do occur, you want to detect them, prevent them from reaching your data plane. So either stop them or detect them. And then the third one is, sometimes things get through your belts, get through your suspenders, maybe even your safety pins and your buttons might get through those safety measures too. So you want to constrain the blast radius in production. And so that's where it comes to partitioning our data plane, our separate network zones or data planes in production. So we have multiple levels of protection against poison pills.
I think one of the other things that you need to do or need to think about when detecting the problem is you got to understand what to do then, right? So you find that a customer has somehow managed to, or some system has managed to inject a change that you can't process. Okay, well, so you have to have a clear methodology for what do I do now? And in our case, at least, we have containers in DNS world called what we call hosted zones, DNS zones, and we apply for customers. We give them a guarantee of ordering and atomicity within a zone, but not for all the other zones. So what we do if we find a piece of poison in a change for one zone is that zone gets sort of sidelined, and we say, okay, we're stopping changes flowing to that zone until such time as we can get an operator involved or whatever we need to do to mitigate that. But everyone else can keep moving. And so having a reasonably small atomic unit that we can pull out and say, okay, you sit on the sidelines for the minute while we keep everyone else moving is pretty important. I think one of the other things that's kind of interesting, and we've done a little bit of for finding these kinds of problems, is fuzz testing. Mm-hmm. And there's different types of poison pills. There's ones that come to the data plane from clients, as well as ones that come from the control plane down to the data plane. Fuzz testing is super useful with a DNS service. There are, it turns out, a lot of different ways to construct a DNS packet, and so we that's a really useful technique for us.
we've sort of learned from, we have experience around that area from years past. Different processes that have ingested DNS replies. So our cache servers trying to do DNS resolutions, receiving values they didn't expect.
Right.
Or trying to do HTTP origin fetches and receiving range values they didn't expect.
Right.
So yeah, all those can be the data plane can be exposed to all those in different ways, like you're saying.
Going back to that topic of change and our global changes, unlike our customer configurations and perhaps some of our own internal configs and code changes, they don't necessarily have to be deployed globally all at once. So Gavin, talk me through what that deployment looks like.
Sure. So in Route 53, I mean, all of our systems, obviously, we need to deliver new features from time to time, apply security patches, all kinds of things. So we need to be deploying pretty regularly and pretty freely. And so the trick is all about keeping deployments moving fast, being able to deploy new features quickly and move fast, but at the same time do it safely. And I think when we go to deploy a service like Route 53, what we think about is two different classes of problems that potentially arise typically with the DNS data plane itself. The first one is the kind of problem we might introduce where we stop answering. So maybe we introduce somehow a crash bug into it, or a regression in performance, so we're not able to keep up anymore and we're dropping some of the queries. So there's that class of not answering bugs, I guess you'd call them. And then there's the second class of it where maybe we've somehow introduced like a subtle logic bug or something, and now we're returning different answers or incorrect answers in some way. Like, so you could imagine within our geolocation routing, we're returning Paris instead of Berlin or something like that. And so for the first class of problems, this 4 data plane story, the redundancy is really good. We can apply that within our deployment mechanisms. So we align our deployment ordering by those data planes. So first of all, we start off by deploying to beta and gamma pops and running a bunch of tests there. And then we will deploy to just one pop somewhere in the world. There's one that always gets the first change. We let that sit for a little while, run a bunch of tests on it, make sure everything's okay, inspect metrics, and then we start on the first data plane. And so we deploy like all 50 pops of the first data plane before we go any further. And again, give that a little bit of time, inspect the metrics. Most of this stuff is automated. We don't manually inspect the metrics. And then only then, when the first data plane is successful, we have the other 3 still sitting there safe, not using this yet. Now we're confident. Now we can say, okay, let's move on to the second, third, and fourth data planes in time. So by aligning our deployment strategy to the redundancy, we can make sure that everyone in the world always has at least those 3 good name servers, even in the worst case that we have some problem surprise us on the first data plane. And the other thing that we do is the other problem that I was talking about is these wrong answer failures, and they're a little harder. The thing that we tend to work on with those is lots and lots of automated testing. When I first started coding, and for longer than I care to admit in my career coding, I manually tested my code changes, and it turns out that just doesn't really scale. And everybody listening probably knows this. So we have tons of unit testing and integration testing and acceptance testing all the way along, to the point that at this point we recently had to give a developer some time to go and optimize the performance of our unit test suites because they were taking so long to run. Mm-hmm. There are huge numbers of tests that are run to every new change at build time for every new change on Route 53. And that's in order, like, it's a complicated enough piece of code. There's a lot going on in there, and you want to check everything is working after that change.
I'd probably add canaries to the list.
Right.
Even in the absence of deploying software, we have canaries running in production that are constantly giving us the signal of availability and healthiness of our service. And we've taken to, in addition to all the tests that Gavin mentioned, taken to using those same canaries and pointing them at our pre-production stage. So that gives us an additional signal of validity before we promote to the next wave. And then we follow similar practices, deploying to one network zone first before the other.
Right.
Last thing I would tack on is automation, right?
Yeah.
Get humans out of the loop.
Right.
Automate your roll forwards and automate your rollbacks.
Yeah.
Code changes, configuration changes, all seem to be driven by humans. How else are we our own biggest threat to availability? Georgie, can you elaborate more on that?
Yeah, of course, we are the biggest threat, right? Gavin gave away our average age here, right? We all have caused multiple outages throughout our career, right? But we like to think that we caused every one of those only once, right? And we made different mistakes as we went along. So a very important part of our job here is to take those learnings, right? To take those outages that we made and create better systems that are not susceptible to those, right? If a human makes a mistake, we don't blame that human. That doesn't lead you to success, because at the end of the day, the maximum you can do is fire that person and hire a new one that's going to make the same mistake likely, right? So instead of that, and I'm lucky that instead of that, because otherwise I wouldn't be here, right? We build new tools that create guardrails around those things, that do not place the eject button next to the deploy landing gear button, right? So that the pilot doesn't make the wrong thing. So it's the same thing. We build tools and build systems that lead to success, that prevent availability problems, right? One very recent example is we're getting out of the business of logging interactively to hosts, right? So if there's a problem, instead of you going to that host, we have tools that gather all the information from that host. Similarly, we don't do SQL queries directly on databases. We have tools that have the queries we need already pre-programmed. And then if you need to get some information from the database, you go to those tools, and those have been proven safe in the past, right? We do not give all these degrees of freedom unnecessarily. We still have them available under a process that we call break glass, right? Get the X from the fire thing on the wall and fight your way out of a fire, right? But similarly, keeping on that analogy, you don't want to walk around in an office building with an axe in your hand. That wouldn't be wise. Yeah. So it's the similar kind of thing. We have the tools if necessary, but we build everything we can to make operations and changes as safe as possible.
In support of that, I often think of it as when a person causes a problem, when a person runs the wrong command or impacts availability in some way, I often think of it as not that person's fault. It's our system's fault for allowing them to have done that. Perhaps we haven't built the right mechanisms, the right protections in place for that kind of scenario.
I think even thinking back to what you were saying before, like one of the great benefits of continuous integration, CI/CD, continuous integration, continuous deployment, is for sure the speed at which you can move. But one of the other great benefits is there are no humans involved. Admittedly, there's somebody to write the code typically, though these days there are even automated systems that can review it and tell you where you may have gone wrong. But we're not manually deploying code anymore.
Right.
And that definitely has caused problems for people in many places in the past.
Right. Just sharing my own experience, I would say 7 years ago or so, I recall deploying software, manually clicking buttons, going through waves. I get to the last one, I click deploy, and I walk away. I go for a one-on-one meeting. It turns out that last wave deployment had broken part of the internet, and things were crashing and burning while I was gone. There were no automated tests. There was no automated rollback. And so that's just an example of a mistake I've made and that we've learned from, which has inspired a lot of the systems we built.
One thing that comes to mind is the fact that our services are always growing and we're operating at this massive scale. We're operating at a bigger scale than yesterday and a smaller scale than tomorrow. How do you make sure you don't unexpectedly hit a limit you didn't know about before or a cliff? And Harvo, subsequently, let's talk about how far in advance for that scale are you having to plan?
Right. Yeah. every single day since our services are growing, every day is a chance for our services to run with a scale they've never seen before. We can take the example of a configuration that we were mentioning earlier, delivering customer configuration to the edge. Perhaps there's some limit that we don't know about. Perhaps there's some maximum number of configuration items that we can ingest. One strategy is to give yourselves a buffer. So if you think you plan for an adoption rate of 1 million entities, go ahead and define 2 million of them, or pick some upper bound. You now have that buffer, and as your adoption rate increases, you simply eat into that buffer. From the perspective of your data plane, they're still dealing with that constant amount of work as your service continues to grow. That's one pattern.
Yeah. I think one of the other ones that's kind of interesting is varying things between harping on the multiple data planes. You can kind of use one of them as a canary for this by varying the limits. So let's say we might be afraid of running out of a file system limit, or the amount of heap memory we're using in an application or whatever. And so by jittering those limits, we can get early warning signs from a minority of the fleet. And if we do that in a way that aligns with with our redundancy silos, what we can say is, okay, well, yeah, when we hit that limit, assuming we do, or if we hit that limit, it'll affect one, but it won't affect the others. And so you can I'll give yourself a lot of room to kind of recover from situations like that.
Right. I think that last comment is interesting because it touches in a topic that is recurrent in that conversation, which is diversity, right? So, of course, you're running every single one of those products is a single service and is running more or less the same code everywhere, right? But we have to create ways for it not to be a monoculture and be everything equal at the same time, because otherwise the same input is going to lead to the same output, right? And if that same output is bad, well, badness is everywhere, and we don't want that. So one example of an extreme example of where we improved on that is on CloudFront's DNS system, right? In front of half of the fleet, we have a separate DNS server that is a caching server, right? So if the main server fails, half the fleet has 90-something% of the queries in cache and can answer from those. Yeah, we might not be 100% available, but the internet might not be down or not fully down, right? But if the caching system has a problem itself and it crashes, the other half of the fleet can answer queries directly, right? So we created that diversity on purpose. We cannot always do that because it has obviously a huge cost. It's not everybody can write multiple copies of your software, not all the software. But the point is diversity. Every way you can think of making your fleet different from one another, even in minute ways like these limits, will help you with availability.
Because you guys even use different languages, like they're completely different code bases, different languages.
Yeah, correct.
Right.
Yeah. One of them is in C, the other one is in Go.
Right.
So changing topics a bit, how does the unpredictability of the internet factor in? Not only can physical things go wrong, such as an undersea cable that's cut, an unexpected customer can have the next piece of content that's going to go global, and millions of our customers around the globe are trying to access that piece of content at the same time. Gavin, how do you protect the services and our customers in these situations?
As a DNS service, Route 53 is subject to a lot of what do we call them? Flash crowds, flash mobs in various forms.
Yeah,
surges and sudden increases in traffic. I think there's kind of a couple of things that we do just off the top of my head. One of them is you kind of, with most of these services, the worst thing that can happen if you get overloaded is that you fail everything. So having some kind of a notion built in or a mechanism built in that says, I know how much this service can handle, or I know how much this node can handle, and therefore I will cheaply drop everything in excess of that. So if you're answering DNS queries and you can handle 50,000 queries per second and 60 show up, you should continue to handle 50,000 queries per second and cheaply drop the other 10, because that's going to be the best outcome that you can get. And so that kind of load shedding technology is very important. Now, needless to say, that doesn't happen very often, but when it happens, that is very important. The other thing that we do in Route 53 for this is relates actually to what Georgie is talking about making diversity between the data planes. We use this technique called shuffle sharding, which Harvo mentioned as well, where essentially all of the customers live on different nodes in each of our data planes as well. So if you look at your name servers, you get 4 rather random looking numbered name servers. That's a very real thing. You're the only customer with those 4. In fact, you're the only zone with those 4 name servers. And it allows us to land your queries to land every zone on every data plane in a different way, which means that if you're beside a flash mob in one data plane, you'll very unlikely be beside the flash mob in the other data plane. And maybe you might find one of your name servers unresponsive while we deal with the flash mob, but because it's DNS, it retries well, the other name servers will keep you going. Shuffle shard, it's a super powerful technique. There's actually an article in the Builders Library, I think Colin wrote it, which is really worth a look. What do you guys have?
All right. I can share another example for how our services deal with unexpected surges in load. The first is I think about Global Accelerator. What it does is it load balances connections that it receives across our customers' endpoints. So our endpoints being EC2 instances or other load balancers within AWS. When there's an unexpected rise in demand, we don't want all that traffic to land on one of our customers' endpoints, have that overloaded, and have the others be idle or underutilized. So what we'll do is we'll distribute traffic in steady state, even before we're at in an overloaded state. The expectation is when we do see that rise in demand, that demand itself is dispersed across all of your endpoints as we go. And Global Accelerator doesn't do this only across your endpoints within a given region, but also across AWS regions themselves. So it's globally distributing. And then we can also bring out the concepts, these similar concepts as they apply to managing traffic across the AWS global network itself. So with the internet control systems that we have, all of our services are delivering bytes out to customers on the internet. We have traffic engineering that we put in place to evenly distribute this traffic across our border egress interfaces to reach clients on the internet, assuming they're within an equivalent band of performance. When there is a surge in demand, we would expect that rise to occur evenly across these interfaces. But then the suspenders to our belt is that we have automated systems that can then take action when there is a surge that our standard distribution isn't able to handle.
Yeah. So something else we do in CloudFront specifically is about handling high-profile events. So CloudFront has 275 POPs around the globe. Right here where we are in Seattle, we have 3 or 4 of them. So imagine we are handling an event like the Super Bowl, which we help deliver. And in that event, we have more people trying to watch the Super Bowl in Seattle than the 4 POPs in Seattle can handle, right? So instead of having a problem, we have a very intricate capacity management system that in real time is always measuring the demand and the performance of every POP to every network. So using those 2 signals, we are able to do a process that we call beam packing, which is similar to the process that we do when we're trying to pack our stuff before traveling, try to fit everything into the bags that the airline is going to allow us to carry, right? So we fit all this demand into each one of the POPs and the best POP possible that still has capacity. And that is dynamic. That happens again every few minutes. We do it again and again and again, right? So that way we ensure that we're serving every customer from their preferred location so they have the highest possible throughput and can watch the game in 4K, right? But also not exceeding the capacity we have there, because at that point we would have problems and would have to load shed, for example, right? And another thing we do is, other than this beam packing system, we have another type of system that is very rapid reaction, that is even faster than that one, that when one specific customer surges in traffic, we disperse that traffic across the nearby locations so that we reduce the chances of impact. So the idea of those two systems is pretty much the same one, which is, look, we have capacity, but we might not have capacity exactly where the traffic is going, right? And that goes in common with the network system that you're talking about. So being able to react and distribute that traffic gives us the best opportunities to handle it. You have to realize that the AWS network that we all share has upwards of 370 terabits per second of peering capacity and growing every day. That number is probably outdated by now, right? So it's not like we run out of capacity ever. That doesn't happen, but we might run out of capacity at one place and then have to spread it around for a little while until we can do the right thing.
Georgie, even with the preparation and inherent benefits that we have built into our systems, things can still go wrong. How do we defend against the unknown?
Right. So that's where it gets interesting, right? So we talked a little bit about that before, right? We talked about the multiple systems, diversity, right? The concept behind all those things is defense in depth, right? Is building it like an airplane. So if you look at the root cause analysis of the failures we have from time to time, they usually look like airplane crashes, right? So this thing went wrong, this person did the wrong thing, this other thing went wrong, that other alarm missed. Like there's a series of things that happen, and well, at the end of the day, you had a little bit of impact, right? And that is by design, right? We decouple systems as much as we can. We build separate data planes. So we build separate DNS servers. So it's this insane amount of redundancy, this insane amount of precautions and thinking about what could go wrong, right? And that's an important part, like thinking about what could go wrong. So think about the work we do here, right? Like keeping the culture of doing the right thing is one of the most important things we can think about. Right? So let me give you one example, right? When we talk about availability, one design pattern that usually comes up in designs is, oh, let me have a fallback, right? I'm going to deploy this to this region, and then I'm going to deploy a copy to the other region. And if that one goes back, I'll fall back to that, or a database, or a storage system, or anything, like fall back to another, right? I'm sure that if you bring that design to me, to Gavin, to Harvo, that design, the first question we will ask you is, well, how are you testing your fallback, right? And why is that? Because we realized over time that if you don't test that fallback, by the time you need it, chances are it's not going to work. The world will have evolved around it, things have changed, and the fallback is not going to work as expected. So if you're not testing it, you might as well not even build it. It's not worth it because it's not going to be there. You're not going to know how to use it, how to engage it, or things like that. Like it's not going to be there, right? And these things have to be hammered, and the culture has to be there, right? So availability is maintained as well as a culture, with a culture.
Yeah.
I think one of the other things that we have is, as well as like culture in terms of how we design things, is also culture in terms of how we operate things. So like any system, we have on calls with pagers, and from time to time at the start of an event like this, of an unexpected event, there's a page going to go off, and someone's going to go and have a look at what the issue is. And so making sure that all of our team as operators have a kind of well-aligned, relatively simple sort of set of principles for how we do things is really, really important. When to engage more people is a really important starting point. Probably the most important thing to know in your first on-call is when you're out of your depth and it's time to get other people. I talked about having hundreds and hundreds and thousands of metrics. We do. Having one relatively simple dashboard that shows you immediately, are customers all okay? Because if that dashboard says anything other than yes, then now it is definitely time to be getting more people involved. And having sort of those simple principles, like there are 4 data planes, we only ever touch one of them at a time. It's a very, very simple metaphor, but it's something that we can easily explain to any new team member, and pretty quickly they start to realize, okay, if I'm ever asked to do more than one, or if someone else is ever proposing to do more than one, I should start asking questions. Why would we do that? And kind of inculcating that culture. Because it's, over time, people move on and more people join, and you can lose that kind of thing very quickly. So it's really important that senior members of the team not only are kind of role modeling this kind of thing, but also really encouraging the newer members to do it as well, so that it's kind of sustainable. Sorry, Harvo, I think I cut across.
Oh, no, that's fine. I think I was just going to add that I think a great strategy is to expect that things are going to fail, and then plan for it, design for it.
Right.
So we've designed for fault isolation. We've designed for making our systems as simple and boring as possible to avoid the different modes of operation that Georgie was mentioning. A great strategy to make fallbacks really work is to not have a separate fallback. Just always do always do your base operation all the time. We spoke about constant work. Just what happens when an entire region fails for Route 53 and health checks?
Right.
You're still doing the same work because you're delivering the same amount of health checks every time.
Yeah.
You're talking about operations, and since I like analogies, and they're talking about planes before, I'm going to make another one there, right? So I like to think that our job as an engineers is very creative, right? We get to design all these things, and hopefully folks watching this video found it interesting, right? That the systems we came up with to do for availability, and that is creative work, right? But when I put away the designer hat and put the hat of operator, I don't want to be creative at all, right? I want to follow the run book. I want to do the things that we discussed about before. And if things go wrong, I want to engage more people or roll back without asking questions, right? And that's exactly how airplanes are done, right? If you're designing a new airplane, you should be very, very creative and design the best airplane you can and more interesting and everything else. But if you're flying an airplane, I don't want my pilot to be creative. Right? And not at all. I want him to follow all the procedures, exactly how they trained on the simulator and everything, because I don't want to crash.
They don't dress like Indiana Jones for a reason, I think, when they're walking on.
There you go.
All right, we've come to the end of our session today. I want to thank the three of you all for your thoughts and for sharing them with the audience. And for those out in the audience, we're going to move now to our live question and answer.